why we have to have a suite of gas giant planets. Those gas giants we see in our solar system play a critical role in shielding the Earth from taking too many hits from asteroid and comet collisions. And the way they're distributed in terms of their mass and distance, it's a very effective shield. But if we were to bring any of those gas giant planets closer, now their gravity would destabilize the orbit of the Earth. Or if we made them more massive, it would destabilize the orbit of the Earth. Or if we made them less massive or more distant, then it would ruin their shielding capability. So we can see all the fine-tuning that exists there. And also we have to have those gas giant planets in appropriate orbits where they don't set up powerful mean motion resonances.
Which are?
Well, let me give you an example. Our solar system did experience a powerful mean motion resonance 3.85 billion years ago. And that was when Jupiter and Saturn were interacting with the Kuiper belt of comets and drifting outward in the solar system. But that comet asteroid belt was much denser at the orbit of Saturn than it was at the orbit of Jupiter. So Saturn moved out more rapidly. And it reached a point where Saturn was making exactly one orbit for every 2 orbits of Jupiter, which meant that, twice in Saturn's orbit, Jupiter would line up with it, and there being the 2 biggest planets, they would exert a strong gravitational tug on the rest of the solar system bodies, especially those at the inner part of the solar system. And bottom line is that resulted in a destabilization of the Kuiper belt, and planet Earth was pelted by nearly 20,000 giant asteroids and comets in a span of a little less than 50 million years.
Wouldn't want to be around then, huh?
Well, actually, that played a crucial role, as you'll see in the next chapter, for making life possible here on planet Earth.
Wow.
It was an important role. But now that you've got life on the planet, you don't want that happening every day.
That's right.
You don't want it happening at all.
Yes.
Because that would be a total extermination event. But fortunately, the gas giant planets have orbits where we don't get those mean motion resonances taking place. Moreover, the inner solar system bodies, Mars and Venus especially, play a role in breaking up the less significant mean motion resonances that are set up by Jupiter, Uranus, Neptune, and Saturn. In fact, even the moon plays a role in the breaking up those resonances. Bottom line is, now that Pluto is off the list of planets in our solar system, every planet plays a role in making possible advanced life here in our solar system. And because we've been doing research on these extrasolar planets, it's actually enhanced our knowledge and insight into the supernatural design of our solar system for our particular benefit. So in that sense, this chapter is a mandate. We really need to do more research. I'm looking forward to when we've discovered 10,000 planets outside of our solar system, because I believe that in making those kinds of discoveries, it's going to give us even more insight into the design of our particular solar system for humanity's benefit, stuff that we don't know today. So that's kind of a prediction I'm laying out there.
Sounds good. Hugh, would people who are skeptical of your model acknowledge fine-tuning then? You're calling it supernatural design. Would they say, yeah, it does look like it's fine-tuned?
Everybody I know who's doing research in this area acknowledges fine-tuning.
Okay.
They're not all saying that Jesus Christ is the fine-tuner, but they do acknowledge the fine-tuning is there and that it needs to be explained.
Okay, so this is part of the test then, one of the components of the model.
We actually have a chapter in the book where we talk about these non-theist astronomers' attempts to bypass Jesus Christ as the explanation and kind of the lengths they go to explain the design we see. So we have a critique of other models coming up.
Okay, we'll look forward to that. What are you going to talk about in the next chapter?
Next chapter, we're actually going to talk about life. I mean, it's kind of interesting. We go 8 chapters or 7 chapters or 8 chapters, I guess,
we're on 8,
getting to life. But the whole point is, if you look at the history of the universe, for over 9 billion years, there's no life in the universe. So it's only in the latter part of the history of the universe that we get life.
So it's all prep time, huh?
It's all prep time, but it's crucial prep time. So in the next chapter, we're going to talk about some of the details of that preparation for life on planet Earth and the origin of life itself.
Okay, Hugh, here we are approaching the middle of the book, I think, chapter 9. And you have taken us from the cosmos, the universe, a little bit closer to galaxies, and now I think you're going to look at Earth. Is that correct?
That's correct.
And some of the fine-tuned characteristics.
Especially life on Earth.
Life on Earth and characteristics for advanced life. You suggest that Earth has a fine-tuned history. I think that's a new term for a lot of people. What do you mean?
Well, not only is the Earth fine-tuned for advanced life, it has an extraordinary history. I mean, we all recognize that you need a planet about the size of the Earth. If it's any less massive, it's not going to retain water. Water will escape to outer space. On the other hand, a planet the size of Earth will form with a huge ocean and a very thick atmosphere. And we may think that having lots of water is a good thing, but too much water means you're not going to have continents. And it's really critical for advanced life that the surface be one where you got oceans and continents together. Without that, you can't recycle the nutrients. So even less primitive life needs to have exposed continental land masses along with the water. Now, in order to make that happen, Earth needs a supernatural transformation event. And so I talk early in Chapter 9 about how astronomers have been able to determine that a planet about the mass of Mars formed along the same orbital path of the Earth at what's called one of the Lagrange points. There's actually 3 places 120 degrees apart along the orbit of the Earth where potentially you could have another body sharing the same orbit. But given the orientation of the gas giant planets and the way they move outward as they interact with the Kuiper Belt and the early history of the solar system, that planet, the size of Mars, will inevitably be destabilized and begin to creep along the orbit and move towards the Earth. But creep is the right word. It winds up getting a low-velocity collision with the Earth at a fairly high impact angle. And that's important because otherwise you'd wind up with the Earth being destroyed. So instead of the Earth being destroyed, we have this Mars-sized planet largely being absorbed into the interior of the Earth. And because it collides with the Earth when it is a very deep ocean, it turns all that water into steam, and that steam blows off the Earth's atmosphere into outer space. Also, most of the water escapes to outer space as a result of the collision. And the collision is also such that it melts the Earth and causes the heavy element material in the collider to sink into the core of the Earth. Then the light element material in both the collider and the Earth get thrown into outer space where they form the moon. Wow. And the moon is critical for advanced life. Without a small planet being orbited by a single gigantic moon, advanced life is not possible. So this extraordinary collision event, extremely fine-tuned, gets rid of the excess water, gets rid of the excess atmosphere, and sets up the moon that's critical for stabilizing the tilt of the Earth's rotation axis, as well as setting up the appropriate tides that allow nutrients to be efficiently recycled in the Earth. So that's what I mean by a special history. Mm-hmm. And we talked a little bit about in the last episode how there was a later event called the Late Heavy Bombardment. Whereas Jupiter and Saturn migrate outward in the solar system, they reach a 1-2 resonance, which results in tens of thousands of colliders hitting the inner solar system planets, and Earth, being the biggest of those inner solar system planets, takes the most damage. And what that does is it allows the Earth's core to be transformed a second time, and it turns out that that second transformation event is crucial for establishing a long-lasting, stable magnetic field and for getting the kinds of plate tectonic activities that will generate the appropriate continents at the right